Voyager 1 is more than 15 billion miles from Earth right now. It has been flying for nearly 49 years. It has crossed the edge of the solar system, entered interstellar space, and it is still whispering data back to us across 23 hours of light travel time. Voyager 2 did the same thing from a different direction. Together, they visited 4 giant planets, discovered active volcanoes on another world, found oceans hidden beneath ice, and rewrote every textbook on the outer solar system. They are the farthest objects humanity has ever built. And here is the question that haunts planetary science to this day. We sent Voyager 1. We sent Voyager 2. So where is Voyager 3? The answer is more complicated, more painful, and more revealing than almost anyone expects. If you enjoy understanding the real stories behind humanity's greatest missions, consider hitting like and subscribing. We dig into the science that actually matters. Now, are you comfortable? Let's begin. Here is a question that sounds so reasonable it barely needs asking. If NASA built Voyager 1 and Voyager 2 in the 1970s, and both spacecraft became the most successful deep space explorers in human history, why did the agency never build Voyager 3? We have better technology now. Better computers, better instruments, better rockets. Nearly 5 decades of additional engineering knowledge. The answer should be obvious. Build the next one. Make it faster, smarter, more capable. Send it further. The fact that this did not happen, that it has not happened in almost half a century, and that no concrete plan exists to make it happen anytime soon, tells a story that most people have never heard. And it begins not with the spacecraft that flew, but with the mission that was supposed to fly instead. A mission so ambitious, so perfectly timed, and so dependent on a freak of orbital mechanics that its cancellation nearly erased the Voyager program from history before it ever launched. In the summer of 1964, a young aerospace engineer named Flandro was working at NASA's Jet Propulsion Laboratory in Pasadena, California. His assignment was straightforward. Calculate trajectories for future missions to the outer planets, Jupiter, Saturn, Uranus, Neptune. The giants that lived in the cold, dark outer reaches of the solar system, hundreds of millions to billions of miles from the Sun. Reaching any one of them was already an enormous challenge. Reaching more than one on a single mission seemed nearly impossible because of the distances and the amount of fuel it would require. Then Flandro noticed something in his calculations that changed everything. The 4 giant planets were drifting into a geometric arrangement that would not repeat for roughly 175 years. By the late 1970s, Jupiter, Saturn, Uranus, and Neptune would be positioned along a gently curving arc on the same side of the Sun. A spacecraft, launched at just the right time, could use the gravity of each planet to accelerate and redirect itself toward the next one, like a billiard ball ricocheting off a series of cushions at exactly the right angles. This technique is called a gravity assist. The spacecraft does not fire its engines to change direction. Instead, it falls toward a planet, accelerates under that planet's gravitational pull, and slings itself outward on a new trajectory at a higher speed. The planet loses an immeasurably tiny fraction of its orbital energy in the exchange. The spacecraft gains an enormous boost. It is one of the most elegant tricks in all of orbital mechanics, and it only works when the planets are in the right positions relative to each other. Flandro's discovery was staggering in its implications. A single spacecraft, launched in the late 1970s, could visit all 4 giant planets in a single continuous journey lasting roughly 12 years. Without the alignment, visiting each planet individually would require separate missions, each taking decades, each burning enormous amounts of fuel, each costing billions. The alignment was a cosmic gift. It turned a series of 4 nearly impossible missions into one extraordinarily difficult but achievable one. And it would not come again until approximately 2154. That is not a typo. The next comparable alignment of the outer planets is over a century away from where we sit today. The window Flandro identified was not just rare. It was the only opportunity anyone alive in the 20th century would ever see. NASA recognized the significance immediately. By the late 1960s, the agency had developed a formal mission concept called the Grand Tour. The plan was breathtaking in its scope. Multiple pairs of spacecraft would be launched across several years, each pair taking a different trajectory through the outer solar system. One pair would visit Jupiter, Saturn, and Pluto. Another would visit Jupiter, Uranus, and Neptune. Together, they would conduct the first comprehensive survey of every major world beyond the asteroid belt. The spacecraft designed for the Grand Tour were called TOPS, an acronym for Thermoelectric Outer Planet Spacecraft. They would carry advanced instruments and be powered by radioisotope thermoelectric generators, devices that convert the heat from decaying plutonium into electricity. Solar panels are useless that far from the Sun. At Jupiter's distance, sunlight is only about 4% as intense as at Earth. At Neptune, it drops below 1/10%. Any spacecraft venturing that far outward would need to carry its own power source, and plutonium was the only viable option. The Grand Tour was the kind of mission that defines an era. It would have been to planetary science what Apollo was to human spaceflight, a statement of capability, ambition, and national purpose. The estimated cost was approximately $750 million in early 1970s money. In the context of the federal budget at the time, it was ambitious, but not outrageous. Then the political ground shifted beneath it. To understand what happened next, you have to understand where NASA stood in the late 1960s and early 1970s. The agency's budget had peaked in 1966 at roughly 4.4% of total federal spending. That number is almost incomprehensible by modern standards. Today, NASA receives less than half of 1%. In 1966, America was racing to the moon, and the national security establishment treated space supremacy as a Cold War imperative. Money flowed. Engineers were hired by the thousands. Facilities were built. Ambition was effectively unlimited. By the early 1970s, that world was gone. The Apollo program had achieved its goal. Neil Armstrong walked on the moon in 1969. The political urgency evaporated almost immediately. The Vietnam War was consuming national attention and federal dollars. The Great Society programs demanded funding. President Nixon's administration adopted a conservative fiscal posture toward the space program. NASA's budget began a steep decline that would not fully stabilize for decades. In this shrinking environment, NASA faced an agonizing choice. The agency needed a major new program to justify its workforce and infrastructure after Apollo. The leading candidate was the Space Transportation System, a reusable space shuttle that would reduce the cost of reaching low Earth orbit. The shuttle was politically attractive because it promised routine access to space, military applications, and commercial satellite launches. It was also enormously expensive to develop. Something had to give. In December 1971, the Grand Tour was cancelled. The funding was redirected to the Space Shuttle program. The top spacecraft were abandoned. The most ambitious planetary mission ever conceived was dead before a single piece of flight hardware had been built. That should have been the end of the story. The alignment was still coming, but there was no mission to take advantage of it. The window would open and close, and humanity would have to wait another 175 years for the next chance. But the engineers and scientists at the Jet Propulsion Laboratory were not willing to let go. What happened next was one of the most remarkable acts of institutional persistence in the history of space exploration. JPL proposed a drastically scaled-down alternative. Instead of the Grand Tour's multiple spacecraft visiting all the outer planets, they would build 2 identical probes and fly them only to Jupiter and Saturn. The spacecraft would be based on the proven Mariner platform, the same design family that had already flown successful missions to Venus, Mars, and Mercury. This would save development time and cost. The 2 probes were initially designated Mariner Jupiter-Saturn, later Mariner 11 and Mariner 12. The cost was reduced to roughly $360 million for development alone, significantly less than the Grand Tour's price tag. The mission was approved in May 1972. It was a shadow of the original vision, but it was alive. The critical detail that the JPL team embedded in the mission design, almost like a hidden seed, was trajectory flexibility. If the first spacecraft, Mariner Jupiter-Saturn 77, completed its primary mission successfully at Jupiter and Saturn, the second spacecraft could be redirected onto a trajectory that would carry it past Uranus and Neptune as well. The Grand Tour would be resurrected, not as a guaranteed plan, but as a contingency, an option that could be exercised only if everything went right. In March 1977, NASA held a competition to rename the mission. The name Mariner Jupiter-Saturn felt wrong for what the mission had become. The spacecraft had evolved far beyond the Mariner heritage. They were larger, more capable, and designed for a far more demanding journey. The winning name was Voyager. It carried a sense of exploration and distance that the Mariner designation could not match, and it erased, at least symbolically, the painful memory of the cancelled Grand Tour. Voyager 2 launched first, on August 20th, 1977. Voyager 1 followed on September 5th. Despite launching second, Voyager 1 traveled on a faster trajectory and reached Jupiter first. The naming reflected arrival order, not launch order. Both spacecraft carried identical instrument suites designed to study the atmospheres, magnetic fields, ring systems, and moons of the giant planets. Each was powered by 3 radioisotope thermoelectric generators carrying plutonium-238. Each was equipped with a 12-foot high-gain antenna, and each carried something that had nothing to do with science at all. A golden phonograph record containing sounds and images from Earth, assembled by a committee chaired by Carl Sagan. Music, greetings in 55 languages, the sounds of wind and surf and birdsong. A message in a bottle, cast into an ocean that no one was sure contained any other ships. Here is what $865 million bought. Voyager 1 arrived at Jupiter in March 1979. In the span of 48 hours around its closest approach, it returned more data about the Jovian system than all previous missions combined. It discovered active volcanoes on the moon Io, making Io only the second body in the solar system known to have active volcanism. It revealed the intricate structure of Jupiter's atmosphere, with storms and cloud bands of staggering complexity. It measured the planet's radiation belts, which were so intense that an unprotected human aboard the spacecraft would have received a lethal radiation dose 1,000 times over. Voyager 1 then continued to Saturn, arriving in November 1980. It discovered new moons, resolved the fine structure of Saturn's rings into hundreds of individual ringlets, and made a close flyby of the moon Titan, revealing a dense nitrogen atmosphere with complex organic chemistry. That Titan flyby was so important that mission planners deliberately chose a trajectory that optimized it, even though doing so deflected Voyager 1 out of the plane of the solar system and made further planetary encounters impossible. Voyager 1's grand tour was over after 2 planets. But Voyager 2 was still flying. Because Voyager 1's primary mission at Jupiter and Saturn had succeeded, the contingency plan activated. Voyager 2 was redirected onto the extended trajectory. It flew past Jupiter in July 1979, past Saturn in August 1981, and then continued outward. In January 1986, it became the first and still the only spacecraft to visit Uranus. It discovered 10 new moons, measured the planet's bizarre magnetic field, which is tilted nearly 60 degrees from its rotational axis, and photographed the moon Miranda, whose tortured surface of massive canyons suggested a world that had been shattered and reassembled by ancient impacts. In August 1989, Voyager 2 reached Neptune. It found a dynamic atmosphere with the fastest winds in the solar system, measured at roughly 1,200 miles per hour. It discovered 6 new moons and observed geysers of nitrogen erupting from the surface of the moon Triton, a frozen world with a surface temperature of roughly -390 degrees Fahrenheit, making it one of the coldest places ever measured in the solar system. The navigation accuracy required to hit the precise flyby point at Neptune after 12 years and more than 4 billion miles of travel was equivalent to sinking a golf putt from a distance of roughly 2,200 miles. Assuming you could make a few small corrections while the ball was rolling. Between them, Voyager 1 and Voyager 2 explored all 4 giant planets, discovered 22 new moons, revealed active geological processes on worlds that were supposed to be dead and frozen, transformed the scientific understanding of ring systems, magnetic fields, and atmospheric dynamics, and produced some of the most iconic photographs in the history of science. The pale blue dot image, taken by Voyager 1 in 1990 from a distance of roughly 3.7 billion miles, showing Earth as a tiny speck of light suspended in a sunbeam, remains one of the most reproduced and emotionally powerful photographs ever captured. And they kept going. Both spacecraft crossed the heliopause, the boundary where the solar wind gives way to interstellar space. Voyager 1 crossed it in August 2012. Voyager 2 followed in November 2018. They became the first, and so far only, human-made objects to leave the protective bubble of the Sun and enter the space between the stars. All of this from a mission that was nearly cancelled. A mission that only existed because a group of engineers at JPL refused to let a rare planetary alignment pass without sending something, anything, to take advantage of it. A mission that was originally approved only for Jupiter and Saturn and reached Uranus and Neptune only because the first spacecraft worked well enough to unlock the contingency plan. The cost of the entire Voyager program from development through the Neptune encounter, including both spacecraft, their launch vehicles, their radioisotope power sources, and all the ground tracking support from NASA's Deep Space Network, was $865 million. Adjusted for inflation to current values, that is roughly $4 billion. For context, that is less than the cost of a single modern sports stadium. It is less than what the United States spends on potato chips in a single year. It is, by any rational accounting, the most extraordinary bargain in the history of human exploration. But embedded in that bargain is a truth that most people miss when they ask why Voyager 3 was never built. The bargain was only possible because of conditions that no longer exist. The planetary alignment that made the Grand Tour feasible was a one-time event on any human timescale. The post-Apollo institutional infrastructure at JPL, staffed by engineers who had learned to design and fly planetary missions at extraordinary speed during the 1960s, was a product of a funding era that had already ended by the time Voyager launched. The plutonium that powered the spacecraft came from Cold War weapons production, a supply chain that would collapse within a decade. The Deep Space Network that tracked Voyager's faint signals across billions of miles had been built for earlier programs and was available for Voyager's use. but it was not expanding. It was, even then, beginning to show the strain of supporting too many missions with too few antennas. And the budget environment that allowed NASA to approve a $750 million planetary mission, then scale it back to $360 million, and then gradually expand it again as the spacecraft kept working, was a relic of an era when planetary science still carried the reflected prestige of Apollo and the competitive urgency of the Cold War. By the time Voyager 2 reached Neptune in 1989, that era was not just fading, it was functionally over. Between the launch of Pioneer Venus in 1978 and the launch of Galileo to Jupiter in 1989, 11 years passed without a single new planetary mission leaving Earth. 11 years. Historians of spaceflight call the 1980s the lost decade of planetary science. The Space Shuttle consumed the agency's attention and budget. The Challenger disaster in 1986 delayed not just shuttle flights, but the entire launch manifest for years, including Galileo, which had been waiting for a shuttle ride since the early 1980s. During that bleak stretch, the only thing keeping planetary science visible in the public imagination was Voyager. Its periodic encounters with new worlds, Jupiter in 79, Saturn in 80 and 81, Uranus in 86, Neptune in 89, provided a lifeline of discovery across a decade when almost nothing else was happening. Voyager did not just explore the outer solar system. It kept the dream of planetary exploration alive during the years when the political and budgetary structures that supported it were crumbling. This is the part of the Voyager story that most people never learn. Voyager was not the confident product of a thriving space program striding outward with purpose and plenty. It was the survivor of a bureaucratic near-death experience, built on a shoestring relative to its original vision, launched into an alignment that would not come again for nearly 2 centuries, and sustained, through 12 years of flight, by a generation of engineers and scientists who understood exactly how rare the opportunity was. They knew. The people who built and flew Voyager understood that this was not the beginning of a grand era of outer solar system exploration. It was a narrow window, a crack in the door that politics and physics had briefly opened and would soon close. They poured everything they had into it, and what they achieved in that window stands as one of the supreme accomplishments of the human species. So when someone asks why NASA never built Voyager 3, the first thing they need to understand is this: Voyager 1 and Voyager 2 almost did not happen at all. The grand tour was cancelled. The alignment was nearly wasted. The mission that flew was a fraction of what was originally planned, rescued from oblivion by institutional stubbornness and engineering brilliance. Building Voyager 3 was never going to be a matter of simply deciding to do it again, because doing it again would require rebuilding from scratch a set of conditions that came together once and then scattered. The alignment is gone. The budget environment is gone. The institutional momentum is gone. The plutonium supply chain that powered the spacecraft was disrupted for decades, and the expectations that any successor would have to meet after the extraordinary success of the original missions are now astronomically high. But this is only the beginning of the answer, because even if you could somehow recreate every one of those conditions, you would still run headlong into a set of engineering, financial, and institutional barriers that make a true Voyager successor far harder than any reasonable person would guess from the outside. Those barriers are what we need to look at next. And when you see them laid out in full, the question shifts from why has NASA not built Voyager 3 to how did NASA ever manage to build Voyager 1 and 2 in the first place? There is a version of this story that seems almost insultingly simple. We built 2 spacecraft in the 1970s with computers weaker than a modern digital watch. They worked for nearly 50 years. Technology has advanced beyond recognition since then. Surely we could build something better, faster, and smarter, put it on a rocket, and send it out to finish what Voyager started. The intuition is overwhelming. It feels so obvious that the question almost answers itself. Just build Voyager 3. What is the problem? The problem is that the sentence "just build" Voyager 3 contains at least 5 separate assumptions, and every single one of them is wrong, not slightly wrong, fundamentally, structurally, expensively wrong. Each one represents a barrier that is not merely difficult to overcome, but that operates on a different scale of difficulty than anything the Voyager team faced in the 1970s. To see why, you have to take the phrase apart and examine what a true Voyager successor would actually require in the real world of modern space exploration. Not the world as we wish it were, but the world as it is. And that world has changed in ways that make the original Voyager missions look less like a template to be repeated and more like an unrepeatable stroke of fortune. The first barrier is the one hiding in plain sight. The planets have moved. When Gary Flandro identified the Grand Tour alignment in 1964, he was describing a geometric configuration of the outer solar system that occurs roughly once every 175 years. Jupiter orbits the Sun every 12 years. Saturn takes 29, Uranus takes 84, Neptune takes 165. For all 4 of these worlds to arrange themselves along a trajectory that a single spacecraft can follow using gravity assists at each stop, their orbital positions have to line up within a narrow range. That alignment was available from the mid-1970s through the mid-1980s. It is now gone. The next comparable window will open in the middle of the 22nd century, around 2152 to 2154. No one alive today will see it. This is not a minor inconvenience. It is a foundational constraint that reshapes the entire problem. Without the alignment, you cannot sling a spacecraft from planet to planet using gravity assists the way Voyager did. You can still visit outer planets individually. You can design a mission to Jupiter or to Saturn or even to Uranus or Neptune. But visiting all 4 in a single continuous journey, the defining characteristic of the Voyager Grand Tour, is not possible with any existing or near-term propulsion technology unless the planets cooperate by being in the right places at the right times. Consider what this means in practical terms. Voyager 2 reached Neptune in 12 years. A dedicated mission to Neptune today, without the benefit of a Jupiter gravity assist optimized for a Grand Tour trajectory, would take significantly longer. Depending on the launch window and the propulsion system, transit times to Neptune range from 12 to 16 years, even with a Jupiter gravity assist, which only works if Jupiter happens to be in a useful position at the time of launch. Some trajectory options take even longer, and that is just to reach a single planet. Visiting all 4 outer worlds sequentially without the Grand Tour alignment would require either multiple separate missions, each with its own spacecraft and its own multi-billion-dollar budget, or a propulsion breakthrough that does not currently exist at the scale needed for a flagship mission. The alignment was not a luxury. It was the engine of the entire concept. Without it, the mission architecture that defined Voyager is simply not available. You can build a probe and send it to the outer solar system, but you cannot replicate the Grand Tour. The word Voyager, in the public imagination, means all 4 planets in a single sweeping arc. Physics does not allow that right now, and it will not allow it again for over a century. The immediate objection to everything just described is technology. Surely modern propulsion can compensate for what the alignment provided. If gravity assists are unavailable, build an engine powerful enough to do the job without them. We have ion drives, we have nuclear propulsion concepts, we have solar sails. The 1970s are not the ceiling of what is possible. This objection sounds devastating. It is not. And the reason it is not reveals one of the most underappreciated facts in all of spaceflight engineering. A gravity assist is not just a helpful push, it is free energy on a scale that no propulsion technology in existence can match. When Voyager 2 swung past Jupiter in 1979, it gained roughly 10 kilometers per second of velocity without burning a single gram of fuel. That is a change in speed equivalent to roughly 22,000 miles per hour, delivered instantaneously by the gravitational field of the largest planet in the solar system. To achieve the same velocity change using onboard propulsion, a spacecraft would need to carry an enormous mass of fuel. The fundamental equation governing this, the Tsiolkovsky rocket equation, is unforgiving. Every kilogram of fuel you add to the spacecraft increases its total mass, which means you need even more fuel to accelerate that additional mass, which adds more weight, which requires still more fuel. The relationship is exponential. For high-velocity missions, the fuel mass required grows so rapidly that it quickly exceeds any practical limit. Consider the numbers concretely. Voyager 2 received gravity assists at Jupiter, Saturn, and Uranus on its way to Neptune. The cumulative velocity gain from those three encounters was roughly 16 kilometers per second. To replicate that gain using the most efficient chemical propulsion available, a spacecraft would need to carry a fuel mass many times its own dry weight. For a probe the size of Voyager, this would mean launching tens of thousands of kilograms of propellant, requiring a far larger and more expensive launch vehicle, and fundamentally changing the mission's cost and complexity. What about more advanced propulsion? Ion drives, which accelerate charged particles to extremely high velocities using electric fields, are far more fuel-efficient than chemical rockets. NASA's Dawn spacecraft used ion propulsion to orbit two different bodies in the asteroid belt, Vesta and Ceres, on a single mission. But ion drives produce extremely low thrust. Dawn's engines generated roughly the force of a single sheet of paper resting on your hand. That is enough to gradually change a spacecraft's velocity over months and years in the relatively gentle gravitational environment of the inner solar system. It is nowhere near enough to replace the massive, instantaneous velocity changes that gravity assists provide at Jupiter and Saturn. An ion-driven grand tour would take decades longer than the Voyager trajectory, possibly 30 to 40 years or more, stretching the mission timeline beyond any reasonable institutional or engineering horizon. Nuclear thermal propulsion, which heats a propellant like hydrogen using a nuclear reactor and expels it at high speed, offers significantly more thrust than ion drives. NASA and the Department of Energy are actively developing nuclear thermal concepts under programs like Draco, the demonstration rocket for agile cislunar operations. But nuclear thermal technology is designed primarily for crewed missions to Mars and cislunar operations. It has never been tested in flight. It remains at least a decade from operational readiness. And even when mature, it would not eliminate the need for gravity assists on a grand tour trajectory. It would supplement them, potentially allowing more flexible timing or faster transit between planets. But it could not replace the cumulative velocity gains of multiple planetary flybys. The physics does not permit it at any plausible technology level available in the near term. Solar sails, which use the pressure of sunlight on large reflective surfaces to accelerate without fuel, are another frequently cited alternative. The Japanese Icaros mission demonstrated solar sail propulsion in deep space in 2010, and the Planetary Society's Light Sail 2 operated successfully in Earth orbit. Solar sails have the elegant advantage of requiring no fuel at all, but their thrust is proportional to the intensity of sunlight, which falls off with the square of the distance from the sun. A solar sail that works beautifully in the inner solar system produces negligible thrust at Jupiter's distance and effectively zero thrust at Saturn, Uranus, or Neptune. A solar sail could potentially accelerate a spacecraft during a close pass by the Sun and then coast outward at high speed, which is part of the interstellar probe concept. But it could not provide the mid-course velocity changes needed to redirect a spacecraft from one outer planet to the next. The bottom line is stark. No existing or near-term propulsion technology can replicate what the planetary alignment gave Voyager for free. The alignment was not a convenience. It was the mission's engine. Without it, the energy budget for a grand tour balloons beyond what any realistic spacecraft can carry, and the timeline stretches beyond what any institution can sustain. Modern engines are better than what the 1970s offered. They are not better enough to overcome orbital mechanics. There is a related point that deserves attention, because it addresses another version of the same objection. Even if you cannot do the grand tour, could you not at least build a single probe with modern instruments and send it to one or two outer planets, calling it Voyager 3 in spirit, if not in trajectory? In principle, yes. But the instruments themselves present their own complications. Voyager carried 10 scientific instruments with a combined mass of roughly 105 kilograms. A modern equivalent designed to study even a single outer planet in the kind of detail that current science demands would be far heavier, far more power-hungry, and far more expensive. Europa Clipper carries 9 instruments with a combined mass several times greater than Voyager's entire science payload. The Dragonfly rotorcraft carries a mass spectrometer, meteorological sensors, seismometers, cameras, and a neutron-activated gamma-ray spectrometer. Each of these instruments represents decades of development and millions of dollars of investment. A spacecraft designed to study 4 different planetary systems, each with radically different characteristics, would need an instrument suite of extraordinary versatility and cost. The era of doing everything with 100 kilograms of instruments and a few thousand words of onboard computer memory is long gone. The second barrier is money, and the scale of the problem is much larger than most people realize. The roughly $4 billion inflation-adjusted dollars that bought both Voyagers and everything needed to fly them was, by any measure, an extraordinary deal. But the cost structure of space missions has changed dramatically since the 1970s, and the reasons are not limited to inflation. Modern flagship missions are far more expensive than their predecessors, even after adjusting for inflation. The Cassini-Huygens mission to Saturn, which launched in 1997 and operated until 2017, cost approximately $3.9 billion over its lifetime. The Europa Clipper mission, which launched in October 2024 aboard a SpaceX Falcon Heavy and is currently en route to Jupiter, carries a total life cycle cost of roughly $5 billion. It is the largest spacecraft NASA has ever built for a planetary mission. Its solar arrays, when fully deployed, stretch the length of a basketball court. It carries 9 scientific instruments optimized for studying a single moon of a single planet, Jupiter's ice-covered ocean world, Europa. Europa Clipper is a remarkable mission, but it is not Voyager 3. It will not visit Saturn. It will not fly past Uranus or Neptune. It will orbit Jupiter and perform 49 targeted flybys of Europa over roughly 4 years. It is a deep, focused investigation of one specific world, designed to answer one specific question: does Europa have conditions that could support life? That question is scientifically profound, but the mission architecture is the exact opposite of Voyager's. Voyager was wide, Europa Clipper is deep. Voyager surveyed an entire region of the solar system in a single pass. Europa Clipper will spend years studying one moon in exhaustive detail. The reason for this shift is not a lack of ambition, it is a response to what scientists learned from Voyager itself. The Voyager flybys revealed that the outer solar system was far more complex and dynamic than anyone had expected. Volcanoes on Io, a possible ocean beneath the ice of Europa, nitrogen geysers on Triton, complex organic chemistry in Titan's atmosphere. Each of these discoveries cried out for follow-up missions with instruments specifically designed to investigate them in detail. The broad survey that Voyager conducted was essential for identifying these targets, but answering the questions Voyager raised requires a different approach entirely. Focused missions, single targets, years of observation instead of hours of flyby. This scientific logic is sound, but it creates an economic trap for anyone who wants a Voyager-style successor. Each focused follow-up mission absorbs a huge share of the Planetary Science Division's budget for years or even decades. Europa Clipper alone consumed a dominant fraction of NASA's planetary science funding during its development. The Dragonfly mission to Titan, a nuclear-powered rotorcraft that will explore the surface of Saturn's largest moon, was selected in 2019 with a cost cap of $850 million under NASA's New Frontiers program. By the time it was formally confirmed in April 2024, its total life cycle cost had ballooned to $3.35 billion. That is roughly 4 times the original cost cap. The reasons include the COVID-19 pandemic, supply chain disruptions, design modifications, and repeated replanning driven by funding constraints. Dragonfly has not yet left Earth. It is scheduled to launch in July 2028 and arrive at Titan in 2034. In the meantime, its budget growth has been so severe that NASA's Office of Inspector General flagged it in a September 2025 audit as absorbing a disproportionate share of the Planetary Science Division's total budget. At a projected $494 million in fiscal year 2026 alone, Dragonfly could consume nearly a quarter of the division's entire allocation. The audit noted that this budget pressure has delayed the next New Frontiers competition, pushing the next New Frontiers launch to no earlier than 2033. Now try to imagine proposing a Voyager-style grand tour in this budget environment. A flagship mission to visit all 4 outer planets would need to carry instruments capable of studying gas giants and ice giants, ring systems and magnetic fields, diverse sets of moons at each stop. It would need to operate for 15 to 20 years or longer. It would need its own radioisotope power system, its own launch vehicle, its own dedicated tracking time on the Deep Space Network. The cost, even by the most optimistic estimate, would be well in excess of $5 billion. More realistic projections would push it toward $8 or $10 billion. That is the kind of number that does not just compete with other planetary missions, it cannibalizes them. A Voyager 3 at that price would effectively shut down most other planetary science for a decade or more. No scientific community wants that trade-off. No NASA administrator wants to propose it. And no Congress wants to fund it when there are more immediately compelling missions, like searching for life on Europa or exploring Titan's organic chemistry, waiting in the queue. The third barrier is one that most people outside the space industry have never heard of: plutonium. Every spacecraft that ventures beyond Mars needs a power source that does not depend on sunlight. Solar panels work beautifully closer to the sun, but sunlight intensity drops off with the square of the distance. At Jupiter, a solar panel receives roughly 4% of the energy it would at Earth. At Saturn, barely 1%. At Uranus and Neptune, solar power was considered impractical for missions until very recently. Europa Clipper is actually the first outer planet flagship to use solar panels, but it can do so only because its enormous arrays were specifically engineered for the reduced light at Jupiter's distance, and because it does not need to go any further out. For anything beyond Jupiter, and for missions that require high reliability in the outer solar system's extreme cold, the standard power source has been the radioisotope thermoelectric generator. RTGs convert the heat produced by the natural decay of plutonium-238 into electricity. No moving parts, no fuel to burn, just the steady warmth of radioactive decay, producing power for decades. Every Voyager spacecraft carried 3 of them. So did the Cassini orbiter, the New Horizons probe to Pluto, and the Curiosity and Perseverance rovers on Mars. The problem is supply. During the Cold War, plutonium-238 was produced as a byproduct of nuclear weapons production. The United States had ample stockpiles. But domestic production of plutonium-238 ceased in 1988. For decades afterward, NASA depended on purchases from Russia, which had its own stockpiles from its weapons programs. That arrangement worked for a time, but it was politically uncomfortable and strategically vulnerable. The United States was dependent on a geopolitical rival for a material essential to its most ambitious space missions. In 2015, the Department of Energy restarted domestic production of plutonium-238 at Oak Ridge National Laboratory in Tennessee, but the ramp-up has been slow. The production target is 1.5 kilograms per year, with an aspirational goal of reaching 5 kilograms per year in the future. A single RTG for a deep space mission requires roughly 4 kilograms of plutonium-238. The Dragonfly mission to Titan will use a multi-mission radioisotope thermoelectric generator, or MMRTG, containing approximately 4.8 kilograms. That is roughly 3 years of current production allocated to a single spacecraft. Now, imagine powering a Voyager-class Grand Tour mission. Voyager 1 and Voyager 2 each carried 3 RTGs. A modern equivalent, designed for a 20-year mission with more powerful instruments and higher data transmission requirements, might need similar or greater power capacity. The plutonium demand for a single such spacecraft could consume most of the country's annual production for several years. And plutonium-238 is needed not just for planetary missions, but for Mars rovers, potential lunar surface missions, and national security applications. Every kilogram allocated to a Voyager successor is a kilogram unavailable for something else. This is not a theoretical constraint. It has already shaped mission selection in concrete ways. When NASA evaluates competing mission proposals, the availability of plutonium-238 is an explicit factor. A mission that requires more plutonium than the projected supply can support is at a serious disadvantage, regardless of its scientific merits. The supply chain for the single most critical material in deep space exploration is a bottleneck that did not exist when Voyager was built. Because Voyager was built during an era when weapons production provided effectively unlimited feedstock. The fourth barrier is communication. And this one is getting worse. The Deep Space Network is NASA's system of ground-based antennas that communicates with spacecraft throughout the solar system and beyond. It consists of 3 facilities spaced roughly 120 degrees apart around the globe. Goldstone in California, Madrid in Spain, and Canberra in Australia. This spacing ensures that at least one station can see any point in the sky at any time, providing continuous coverage for deep space missions. The DSN was designed in the early 1960s during the same era of abundant funding that produced Apollo and the original planetary programs. Its largest antennas are 70-meter dishes, massive structures that can detect signals so faint that the power arriving at the antenna from a spacecraft at Voyager's distance is roughly 10 to the negative 16th watts. That is 20 billion times less power than the energy consumed by a modern digital wristwatch. The sensitivity required to maintain contact with spacecraft at these distances is genuinely extraordinary. But the DSN is also stretched to its operational limits. The number of deep space missions relying on the network has grown dramatically since the 1970s, while the network itself has not expanded proportionally. Mars, orbiters and rovers, Jupiter missions, asteroid probes, solar observatories, lunar missions, and interstellar spacecraft all compete for antenna time. Scheduling conflicts are routine. Missions sometimes have to wait hours or days for their allocated communication windows. And the network is aging. The 70-meter antennas at each complex date back decades. Maintenance is constant and costly. Upgrades to individual antennas can take months, during which the missions that depend on them must either wait for narrow communication windows or go without contact entirely. The network was built for an era when a handful of missions shared the sky. It now supports dozens simultaneously, and every major maintenance cycle creates cascading scheduling pressure across the entire portfolio. A Voyager-class Grand Tour mission would need dedicated DSN tracking time for 15 to 20 years or more. During planetary encounters, when data rates spike and navigation precision is paramount, the spacecraft would require priority access to the largest antennas for extended periods. Every hour of DSN time devoted to a Grand Tour mission is an hour unavailable for every other mission in the network. In the 1970s, when the mission queue was shorter and the network was younger, this was manageable. Today, with dozens of active missions competing for the same finite resource, it is a serious operational constraint. There is a fifth barrier that is less tangible but no less real. It is the barrier of time. A Voyager-style Grand Tour would take at least 15 years from launch to final encounter, and that is an optimistic estimate without the Grand Tour alignment. Development would add another decade or more before launch. From initial concept to the final planetary flyby, a modern Grand Tour program could easily span 25 to 30 years. Think about what that means for the people involved. An engineer who joins the project at age 30 would be in their mid-50s or older before the spacecraft reaches its last target. A graduate student who writes their thesis proposal around the mission's early science goals would be a senior professor, possibly retired, before the data arrives. A congressional appropriator who votes to fund the mission in year one will almost certainly not be in office when the spacecraft reaches Neptune. This is not just a human interest story, it is a structural problem. NASA missions require sustained political support across multiple presidential administrations and dozens of congressional budget cycles. Every year, the mission's funding must survive a new round of budget negotiations, each influenced by shifting political priorities, economic conditions, and competing demands. The Voyager program benefited from a relatively compact timeline. The primary mission from launch through the Neptune encounter was 12 years, and the two-planet baseline that was actually approved initially was only about 4 years. A modern Grand Tour with a 20-year cruise phase would need to survive at least 5 presidential administrations and 10 congressional sessions. History suggests that is extremely difficult. The Dragonfly mission provides a vivid illustration. Selected in 2019 with a launch date of April 2026, it has already been replanned 4 times, delayed by more than 2 years, and seen its cost nearly quadruple. And that mission has not yet left the ground. Now imagine the political and budgetary turbulence that a 30-year Grand Tour program would have to endure. Budget cuts proposed by one administration, sequestration imposed by another, a global pandemic, a financial crisis, a shift in national priorities toward lunar exploration or crewed Mars missions. The Voyager team navigated a 12-year primary mission through one of the most turbulent periods in NASA's history, including the Challenger disaster and the lost decade of planetary science. They succeeded through a combination of extraordinary engineering, institutional tenacity, and sheer good luck. Asking a modern team to sustain a program twice as long through an environment that is, in many respects, even more hostile to long-duration science missions, is not a question of capability. It is a question of institutional endurance on a scale that has never been tested. Each of these barriers, the alignment, the cost, the plutonium, the communication infrastructure, the timeline, is formidable on its own. Together, they form an interlocking system of constraints that makes a true Voyager successor qualitatively different from any individual mission in NASA's current portfolio. It is not that any single problem is unsolvable. It is that solving all of them simultaneously, within a single program, under real-world budget and political conditions, requires a level of convergence that does not currently exist and shows no signs of emerging. There is one additional factor that deserves mention, because it operates quietly in the background of every mission selection decision NASA makes. It is the question of risk. Voyager was designed for a 5-year mission. Everything beyond Saturn was a bonus. If Voyager 2 had failed at Uranus, the primary mission would still have been considered a complete success. That framing gave the program enormous psychological and political protection. Every additional planet was pure upside. Nobody had promised Uranus and Neptune. Nobody had budgeted for them. Nobody's career depended on them. The pressure was entirely positive. Look what we accomplished beyond the plan. A modern Grand Tour mission would not enjoy that luxury. If you propose a $10 billion flagship to visit all 4 outer planets over 20 years, every one of those planets is in the mission requirements document. Every one is a promised deliverable. If the spacecraft fails at Saturn, you have not overachieved on a 2-planet mission. You have underdelivered on a 4-planet flagship. Congressional hearings follow. Careers are damaged. The institutional lesson learned is to never again propose something so ambitious and so fragile. The asymmetry between Voyager's framing and a modern Grand Tour's framing is enormous, and it profoundly shapes what NASA is willing to propose. The closest thing to a Voyager successor currently under study is the interstellar probe concept developed by the Johns Hopkins Applied Physics Laboratory. This proposed mission would launch in the mid to late 2030s, use a Jupiter gravity assist combined with a close solar flyby and propulsive maneuver to achieve speeds of roughly 6 to 7 astronomical units per year, and travel outward to distances of 1,000 astronomical units or more within 50 years. It has been called Voyager on steroids by some of its proponents. It would study the heliosphere, the interstellar medium, and potentially fly by a Kuiper Belt object on its way out. But the interstellar probe is not a grand tour. It is an outward sprint. It would not loop through the outer planets one by one, collecting close-up data at each stop. It would pass through the outer solar system on a fast trajectory, gathering what data it could on the way, but primarily aimed at reaching interstellar space far more quickly and with far better instruments than the Voyagers carried. It is an important and compelling mission concept, but it does not fill the role that Voyager 3 occupies in the public imagination. And even this concept has not been formally proposed to NASA for funding. It remains a study, a set of engineering analyses and scientific rationale documents, waiting for a decadal survey recommendation and an appropriations process willing to support it. The path from concept study to launched spacecraft is long, uncertain, and littered with the wreckage of missions that did not survive the journey. What all of this reveals is something that the phrase, "just build Voyager 3", completely fails to capture. The gap between the original Voyager missions and a hypothetical successor is not a gap of technology. We have better instruments, better computers, better materials. The gap is structural. It exists in the orbital mechanics of the solar system, in the economics of modern space exploration, in the supply chain for nuclear fuel, in the capacity of the communication network, in the political durability of long-duration programs, and in the institutional risk calculus that determines which missions actually make it from concept to launch pad. Voyager was not built in a vacuum. It was built inside a specific set of historical conditions that provided, for a brief window, the right alignment of planets, money, infrastructure, fuel, and institutional will. Each of those conditions has since changed. Some have disappeared entirely, and no amount of nostalgia or technological progress can substitute for conditions that simply no longer exist. But there is an even deeper layer to this story. Because the barriers we have just examined, the planets, the money, the plutonium, the antennas, the timeline, are all, in a sense, engineering problems. Hard ones, but still problems that could theoretically be solved with enough resources and enough will. The real reason Voyager 3 does not exist goes beyond engineering. It lies in a fundamental shift in how NASA thinks about exploration itself, a shift in philosophy that changed the kinds of missions the agency is willing to build, the way it selects them, and the logic it uses to decide what is worth doing in the first place. That shift happened in the years after Voyager, and it reshaped everything that followed. If you had walked into the Jet Propulsion Laboratory in 1972 and asked how NASA chose which planetary missions to fly, the answer would have been deceptively simple. A small group of scientists and engineers identified the most compelling scientific targets, designed missions to reach them, and lobbied NASA headquarters and Congress for the money. The process was informal, personality-driven, and heavily influenced by institutional relationships, political connections, and the raw, persuasive power of charismatic advocates. The Grand Tour was conceived this way. Voyager survived cancellation this way. The entire golden age of planetary exploration in the 1960s and 70s was propelled by a relatively small community of visionaries who knew each other, trusted each other, and operated within an agency that still carried the momentum and prestige of Apollo. That world no longer exists, and its disappearance is one of the most important reasons Voyager 3 was never built. The transformation began in the wreckage of the 1980s, the lost decade of planetary science. When Voyager 2 reached Neptune in August 1989, it was the only planetary mission NASA had launched in over a decade. The pipeline behind it was nearly empty. Galileo, the Jupiter orbiter, had been stuck in development hell since the late 70s, delayed by shuttle manifest problems, the Challenger disaster, and redesigns forced by safety concerns about launching a plutonium-powered spacecraft on a crewed vehicle. The Mars Observer, a relatively modest orbiter, would not launch until 1992, and it would be lost catastrophically 3 days before reaching Mars in what investigators concluded was most likely a fuel system failure. The community that had built Voyager looked around at the end of the 80s and saw a landscape of institutional carnage. Careers had stalled. Graduate students had left the field for lack of mission opportunities. International competitors, especially the European Space Agency and the Soviet Union, were flying missions while America sat idle. Something was structurally broken about the way NASA selected and funded planetary science, and the diagnosis was clear. The agency had become too dependent on a small number of massive, expensive flagship missions. When those flagships were delayed or cancelled, the entire field went dark. There was no middle ground, no portfolio of smaller missions that could keep the science moving and the workforce employed while the big projects fought their way through the budget process. The response to this crisis reshaped planetary exploration permanently. It came in 2 parts, and together they created the institutional framework that governs everything NASA does in planetary science today. The first part was the creation of a tiered mission architecture. Instead of betting everything on one enormous project at a time, NASA established 3 categories of planetary missions, each with different cost ranges, different levels of institutional oversight, and different competitive structures. At the top are flagships. These are the grand, once-in-a-generation missions that cost multiple billions of dollars, take decades to develop, and tackle the most ambitious scientific questions available. Cassini-Huygens was a flagship. Europa Clipper is a flagship. They are directed by NASA headquarters, managed by major centers like JPL or the Applied Physics Laboratory, and funded through dedicated line items in the agency's budget. Below the flagships are New Frontiers missions. These are competed through open announcements of opportunity, where teams of scientists and engineers from across the country submit proposals that are evaluated on scientific merit, technical feasibility, and cost. The cost cap for New Frontiers missions is roughly $1 billion, though, as Dragonfly's experience demonstrates, actual costs frequently exceed the cap by wide margins. New Horizons, the Pluto flyby mission, was a New Frontiers selection. Juno, the Jupiter Polar Orbiter, was another. OSIRIS-REx, the Asteroid Sample Return mission, was a third. Dragonfly is the fourth. At the bottom tier are Discovery missions. These are smaller, faster, and cheaper. The cost cap is approximately $500 million. Discovery missions are also competed, with even more emphasis on staying within budget and on schedule. Past Discovery selections include the Messenger mission to Mercury, the Dawn Asteroid Belt Explorer, the InSight Mars Lander, and the Lucy and Psyche asteroid missions. This tiered system was designed to solve exactly the problem that had crippled planetary science in the 80s. By maintaining a pipeline of smaller and medium-sized missions alongside the occasional flagship, NASA could ensure that science kept flowing even when big projects were delayed. It was a rational, thoughtful, and ultimately successful reform. The pipeline of planetary missions in the 21st century has been vastly more productive than the drought of the 1980s. But it also created a structural environment in which a Voyager-style Grand Tour became almost impossible to propose. Consider where a Grand Tour would fit in this architecture. It is too expensive for New Frontiers. The cost of a multi-planet outer solar system mission with a 20-year cruise phase and instruments capable of studying 4 radically different planetary systems would blow through the New Frontiers cost cap by a factor of 5 or more. It does not fit Discovery at all. That leaves the flagship category, where it would have to compete with missions like Europa Clipper and whatever comes after it for the single most expensive line item in the Planetary Science Division's budget. The problem is that flagships are rare. NASA typically flies one flagship planetary mission at a time, sometimes with long gaps between them. Between the end of the Cassini mission in 2017 and the launch of Europa Clipper in 2024, there was no active flagship mission in development for the outer solar system. The next flagship after Europa Clipper is still being debated. Candidates include a Uranus orbiter and probe, which was recommended as the highest priority flagship by the 2023 Planetary Science Decadal Survey, and the Mars Sample Return mission, which has been plagued by cost overruns so severe that its design is being fundamentally reconsidered. This brings us to the second part of the institutional transformation, the Decadal Survey. Every 10 years, the National Academies of Sciences, Engineering, and Medicine convene a panel of leading researchers to assess the state of planetary science and recommend priorities for the next decade. These Decadal Survey reports are not just academic exercises. They carry enormous weight within NASA and Congress. The agency uses them as its primary roadmap for mission selection. Congress frequently references them when making funding decisions. If a mission is endorsed by the Decadal Survey, its chances of being funded increase dramatically. If it is not endorsed, its chances are close to zero. The Decadal Survey process is rigorous, transparent, and fundamentally democratic within the scientific community. It involves years of input from hundreds of researchers, dozens of white papers, and extensive engineering analysis of mission concepts. It is, by most accounts, one of the best priority-setting processes in all of government science. But it also embeds a set of constraints that work against a Voyager-style mission. The Decadal Survey operates on a 10-year planning horizon. It recommends missions that can be started, developed, and launched within that window. A Grand Tour mission with a 25 to 30-year development plus flight timeline does not fit cleanly into this framework. Its development would span 3 decadal survey cycles. Its scientific returns would not arrive until researchers who were not yet born when the mission was proposed are established in their careers. The process is not designed for programs that operate on generational timescales. The most recent decadal survey, published in April 2022 under the title Origins, Worlds, and Life, identified a Uranus orbiter and probe as the highest priority new flagship mission for the coming decade. This was a significant moment for outer solar system science. Uranus has not been visited since Voyager 2's flyby in January 1986, a single encounter lasting only a few hours. Almost everything we know about the 7th planet comes from that one brief passage 40 years ago. A dedicated orbiter would spend years studying Uranus's bizarre magnetic field, its tilted axis, its ring system, its 27 known moons, and its atmospheric composition. The Uranus orbiter is an important and scientifically compelling mission. It is also not Voyager 3. It would visit one planet. It would orbit that planet for years, conducting the kind of deep, focused investigation that Voyager's brief flyby could never achieve. It represents the modern philosophy of planetary exploration taken to its logical conclusion. Go to one place, study it thoroughly, answer specific questions that the flyby missions identified decades ago. This philosophy is sound. It has produced extraordinary science. Cassini spent 13 years orbiting Saturn and transformed our understanding of the planet, its rings, and its moons. The Huygens probe, built by the European Space Agency and carried to Saturn aboard Cassini, landed on Titan in January 2005 and returned the first images from the surface of a world in the outer solar system. Juno has been orbiting Jupiter since 2016 and has revealed the internal structure of the planet in unprecedented detail. These missions are Voyager's scientific descendants. They exist because Voyager showed us where to look. The fight to keep outer solar system exploration alive after Voyager is a story of near-death experiences so severe that any one of them could have permanently ended the endeavor. Each of the missions that eventually flew to the outer planets, Galileo, Cassini-Huygens, and New Horizons, survived its development only through combinations of institutional stubbornness, scientific advocacy, and political luck that came perilously close to failing. Galileo is the most harrowing example. The mission to orbit Jupiter and drop a probe into its atmosphere was first conceived in the early 1970s, around the same time Voyager was being designed. It was approved for development in 1977, the same year the Voyagers launched. The original plan called for a launch aboard the space shuttle in 1982, using a powerful upper stage called the Centaur to send the spacecraft directly to Jupiter. That timeline slipped almost immediately. Technical problems pushed the launch to 1984, then to 1985. Then the Challenger disaster in January 1986 grounded the entire shuttle fleet and forced NASA to reassess the safety of carrying a liquid-fueled Centaur upper stage inside the shuttle's cargo bay. The Centaur was cancelled for shuttle use. Without it, Galileo needed an alternative way to reach Jupiter. The solution was a far less powerful solid-fuel upper stage called the inertial upper stage, which could not send Galileo directly to Jupiter. Instead, The spacecraft would need multiple gravity assists, flying past Venus once and Earth twice over a period of years to gradually build up enough velocity. This Vega trajectory, Venus-Earth-Earth gravity assist, extended the cruise phase from 2 years to 6. Galileo finally launched in October 1989, 12 years after its approval, and did not reach Jupiter until December 1995. From concept to arrival, the program spanned more than 2 decades. During those decades, Galileo endured constant budget threats, redesigns, and technical failures. Its high-gain antenna, a large umbrella-like dish designed to transmit data at high rates, failed to fully deploy during the cruise phase. Engineers were never able to fix it. The entire Jupiter orbital mission had to be conducted using a low-gain antenna with a data rate less than 0.1% of what had been planned. Scientists and engineers at JPL performed extraordinary feats of data compression and mission replanning to salvage the science, but the high-gain antenna failure meant that Galileo returned a fraction of the data it was designed to collect. Despite all of this, Galileo made transformative discoveries, including the strongest evidence to date for a liquid water ocean beneath the ice crust of Europa, the discovery that first put Europa on the map as a potential abode for life. Cassini-Huygens, the Saturn orbiter and Titan lander, had its own near-death experience, but this one came from an entirely different direction: public opposition. Cassini carried roughly 33 kilograms of plutonium fuel in its 3 radioisotope thermoelectric generators, more nuclear material than any previous NASA mission. When the spacecraft was scheduled for launch in October 1997, organized protest groups campaigned aggressively against it, arguing that a launch failure could scatter plutonium across populated areas. Protests were held at Cape Canaveral. Lawsuits were filed. Members of Congress were lobbied to cancel the mission. Some advocacy groups demanded that NASA abandon the use of nuclear power sources entirely. NASA conducted exhaustive safety analyses demonstrating that the risk of plutonium release was extraordinarily small, and that the RTGs were designed to survive launch vehicle explosions intact. The agency ultimately prevailed, and Cassini launched successfully. But the political battle consumed institutional energy and attention that could have been directed toward science. And it established a precedent that haunts nuclear-powered missions to this day. Every mission that carries plutonium must navigate not only the technical and budgetary challenges of spaceflight, but also the political challenge of public opposition to launching radioactive material. The Dragonfly mission to Titan, which will carry a multi-mission radioisotope thermoelectric generator, inherits this legacy directly. New Horizons, the mission that flew past Pluto in July 2015, faced a different kind of existential threat: repeated cancellation attempts driven by budget pressure. The mission was first proposed in the early 2000s after a previous Pluto mission concept called Pluto Express and later Pluto Kuiper Express was cancelled in 2001 due to cost overruns. The planetary science community, led by Alan Stern and supported by a broad coalition of researchers, mounted an intense lobbying campaign to save Pluto exploration. A new, cheaper mission concept was developed and proposed under the New Frontiers program. Even after selection, New Horizons was nearly killed multiple times during the annual appropriations process. In 2002 and 2003, the Bush administration's budget proposals repeatedly zeroed out funding for the mission. Each time, the scientific community mobilized to restore funding through congressional intervention. The mission survived by the thinnest of margins year after year during its development phase. It finally launched in January 2006 aboard an Atlas V rocket with a remarkably tight budget of approximately $700 million. The pattern across all 3 missions is consistent and sobering. Galileo took over 20 years from concept to arrival and suffered a crippling hardware failure. Cassini survived public protests that could have grounded it permanently. New Horizons was nearly cancelled 3 times before it ever reached the launch pad. These are the missions that the public remembers as triumphs, and they were triumphs. But behind each triumph is a story of institutional combat so grueling that the survival of the mission was never assured until the moment the rocket cleared the tower. Now, multiply that level of difficulty by 4 planets, 20 years of flight time, and a budget that would dominate the planetary science division for a generation. That is what a Voyager-class Grand Tour would require in the current institutional environment. Not just technical brilliance, which the community has in abundance, but political survival across a timeline so long and through a budget environment so volatile that history offers no precedent for success. Every outer solar system mission since Voyager has been a knife fight. A Grand Tour would be a knife fight, sustained for 3 decades against opponents who change with every election cycle, in an arena where the rules are rewritten every year. But they are architecturally opposite to Voyager. Each one represents a massive investment of money, time, and institutional energy directed at a single target. And each one, by absorbing a large share of the planetary science budget during its development, makes it harder to propose additional ambitious missions during the same period. The Dragonfly story is the most vivid illustration of this dynamic. Dragonfly's cost grew to roughly 4 times its original cap before the spacecraft ever left the ground. But the budget numbers alone do not capture the structural damage. What matters for the Voyager question is what happened to everything else in the pipeline, while a single New Frontiers mission consumed an ever-growing share of available funds. Other mission concepts that might have competed in the next selection cycle were effectively frozen. Scientists who had spent years developing proposals for new outer solar system investigations were told to wait. The entire rhythm of the competitive selection process, the engine that keeps the planetary science portfolio moving, was disrupted by the gravitational pull of a single over-budget project. And Dragonfly is a modest mission by flagship standards. It targets 1 moon of 1 planet. The structural damage a full Grand Tour flagship would inflict on the rest of the portfolio would be proportionally greater and would last proportionally longer. This is the structural trap. Every ambitious outer solar system mission that flies makes the next ambitious mission harder to start because it absorbs the money and institutional attention that would be needed to develop and launch the next one. Voyager avoided this trap because both spacecraft were built simultaneously under a single program and launched within 16 days of each other. There was no gap between missions. There was no period where the budget for Voyager 2 had to survive a decade of appropriations fights while Voyager 1 was still in flight. The paired architecture and the rapid timeline were essential to the program's survival. A modern Grand Tour could not replicate this. A single flagship spacecraft designed for a 4-planet tour would take at least 10 years to develop, cost somewhere between $5 and $10 billion, and absorb the dominant share of NASA's planetary science funding for its entire development phase. During that period, there would be little room for other flagship missions, severe constraints on New Frontiers and Discovery selections, and constant political vulnerability to budget cuts. The entire planetary science portfolio would become hostage to a single program. NASA learned this lesson the hard way with the James Webb Space Telescope. Webb was originally estimated to cost $1 billion and launch in 2007. By the time it actually launched in December 2021, the cost had grown to $10 billion. During the long years of Webb's development, its budget overruns consumed funding that had been planned for other astrophysics missions. The astrophysics community lived through its own version of the lost decade, watching helplessly as Webb ate through resources meant for the next generation of space telescopes. The experience left deep institutional scars. No one at NASA wants to repeat it. And proposing a 20-year, multi-billion-dollar Grand Tour mission would raise exactly the same fears. This is why later missions to the outer solar system, as important and scientifically revolutionary as they are, cannot be called Voyager 3. They are answers to Voyager's questions, not continuations of Voyager's approach. Voyager was a reconnaissance mission. It went everywhere and looked at everything, trading depth for breadth. The missions that followed, Galileo, Cassini, New Horizons, Juno, Europa Clipper, and eventually Dragonfly and the Uranus orbiter, are follow-up investigations. They go to one place and look deeply. The public does not always appreciate this distinction. When Europa Clipper launched in October 2024, some coverage framed it as a spiritual successor to Voyager. In a sense, it is. It carries the legacy of curiosity and ambition that Voyager embodied. But it is not the same kind of mission. It does not carry the same relationship to the solar system as a whole. And it does not satisfy the specific longing that the phrase Voyager 3 evokes. The longing for a single spacecraft that sweeps through the outer darkness, visiting world after world, each encounter revealing something unexpected, each flyby a new chapter in a story that unfolds across years and billions of miles. That longing points to something real. The Grand Tour was not just a trajectory, it was a narrative. It gave the public a story to follow across 12 years. Each planetary encounter was an event, a moment when the entire world paused to see what Voyager had found. The flyby of Jupiter's volcanic moon Io, the discovery of spokes in Saturn's rings, the shattered surface of Miranda at Uranus, the geysers of Triton at Neptune. These were plot points in a drama that built and built, each revelation more surprising than the last, each encounter further from home and deeper into the unknown. No modern mission architecture replicates that experience. A Uranus orbiter will produce extraordinary science over years of careful observation. But it will not have the narrative momentum of a spacecraft racing from one unknown world to the next. A Europa Clipper flyby campaign will generate data of staggering depth and complexity. But it will not have the feeling of a journey, of a machine moving outward through the solar system, crossing thresholds that had never been crossed before. This is not a criticism of modern missions. It is an observation about the nature of exploration. Some forms of exploration are inherently more narratively powerful than others. The first traverse of an unknown territory, the first survey, the first look, carries an emotional and cultural weight that subsequent investigations, no matter how scientifically superior, cannot fully match. Voyager was the first look. Everything since has been looking more closely. Both are essential, but they are not the same thing. There is one more dimension to the institutional story that needs to be examined, and it concerns the broader trajectory of NASA's budget and political support. Because even if a Grand Tour mission was scientifically compelling, technically feasible, and architecturally coherent, it would still need to survive the budget environment that has defined NASA for the past 3 decades. And that environment has been growing steadily more hostile to exactly the kind of long-duration, high-cost, uncertain return investment that a Voyager successor would represent. NASA's total budget as a share of federal spending peaked at roughly 4.4% in 1966. By the time Voyager launched in 1977, it had fallen to roughly 1%. By the mid-2000s, it was below 0.5%. In recent years, the absolute dollar amount has hovered around $25 billion, which sounds large until you consider that it funds everything NASA does: human spaceflight, Earth science, astrophysics, heliophysics, planetary science, aeronautics, technology development, and institutional overhead. Planetary science receives a subset of this total, roughly $3 to $4 billion per year in recent budgets. That number is now under direct threat. In May 2025, the White House released a fiscal year 2026 budget request that proposed a 24% cut to NASA's overall budget. Congress ultimately rejected most of the proposed cuts in the January 2026 budget resolution. But the fiscal year 2027 request, released in April 2026, proposed a 23% overall cut and a 47% reduction to the Science Mission Directorate, the division that funds all of NASA's space science, including planetary exploration. If enacted, cuts of that magnitude would not just prevent new flagship missions from being proposed, they would threaten missions already in development. Dragonfly, the Mars Sample Return Program, and potentially even ongoing operations of missions like Europa Clipper and New Horizons could face funding disruptions. In an environment where existing missions are fighting for survival, the idea of proposing a new multi-billion-dollar Grand Tour mission is not ambitious. It is disconnected from institutional reality. The Voyager team operated in a declining budget environment too. NASA funding fell steadily through the 70s and 80s, but the decline was from a peak so high that even the reduced budgets of the Voyager era were generous compared to today's allocations. More importantly, the Voyager team had a crucial advantage that no modern team would possess. The spacecraft were already built and flying. Canceling an operating mission is politically and institutionally much harder than refusing to start a new one. Voyager survived the lost decade in part because cutting off communication with a functioning spacecraft that was returning revolutionary data would have been an act of obvious waste. It would have saved almost nothing while destroying something irreplaceable. A new Grand Tour mission would not have that protection during its long development phase. It would be a line item in a budget request, vulnerable to every economic downturn, every political shift, every competing priority. For 10 to 15 years before launch, it would have to survive annual appropriations, fights with nothing to show but engineering studies and hardware in various stages of fabrication. The Dragonfly experience demonstrates how difficult this is, even for a mission with strong scientific support and a much smaller initial cost estimate. The interstellar probe concept, the closest thing to a Voyager successor currently under study, illustrates the institutional side of this problem with painful clarity. The science case is strong. The engineering is plausible. The Applied Physics Laboratory has invested years of careful study into it. And yet the concept was not specifically recommended as a flagship mission by the 2022 Decadal Survey, which instead prioritized the Uranus orbiter. It remains a concept study, waiting for a future Decadal Survey to elevate it and a future budget environment to fund it. That wait could easily stretch another decade. The Decadal Survey that might endorse it will not be published until the early 2030s. By the time funding could realistically begin, the engineers who designed the current concept may have moved on. The institutional memory that holds the study together will have to be rebuilt. This is the quiet way ambitious missions die. Not through dramatic cancellation, but through indefinite deferral, each delay eroding the coalition of advocates needed to push it across the finish line. And even if the interstellar probe survives this process and eventually flies, it will not be a grand tour. It will be a fast outward sprint, not a planet-by-planet survey. The gap between what the interstellar probe would do and what Voyager 3 means in the public imagination remains as wide as ever. The gap between the interstellar probe and Voyager 3, as the public imagines it, is instructive. The public wants the grand tour, the sweeping journey through the outer solar system, each planet a destination, each encounter a revelation. What the scientific and engineering community can realistically propose given the constraints of budget, timeline, orbital mechanics, and institutional capacity, is something different, targeted, focused, deep rather than wide, important but not the same. The modern logic of deep space exploration is not wrong. It produces better science per dollar than the flyby approach Voyager pioneered. It answers questions with precision instead of raising them in passing. It has given us Cassini's 13 years at Saturn, Juno's ongoing investigation of Jupiter's interior, Europa Clipper's focused search for habitable conditions beneath an ice shell, and Dragonfly's audacious plan to fly a helicopter on a moon of Saturn. These are extraordinary missions by any standard, but they emerged from a system that was explicitly designed to prevent the conditions that made Voyager possible. The tiered mission architecture, the decadal survey process, the cost caps, the competitive selections, the risk management frameworks, all of these are rational responses to the institutional failures of the 1980s and 90s. They work, they produce results, and they are structurally incompatible with the kind of sweeping, risky, once-in-a-generation gamble that the Voyager Grand Tour represented. The absence of Voyager 3 is not an oversight. It is an outcome. The system that governs modern planetary exploration was built, consciously and deliberately, in a way that makes a Voyager-style mission almost impossible to propose, almost impossible to fund, and almost impossible to sustain through the decades-long development and flight timeline it would require. The question that remains is whether this outcome tells us something deeper than institutional history. Whether the absence of Voyager 3 is simply the predictable result of changed priorities and constrained budgets, or whether it points to something more fundamental about the nature of exploration itself. About how rare certain kinds of achievements really are, and how difficult it is for a civilization to recognize, in the moment, that it is standing on a summit it may not reach again. That question is what waits in the final chapter, and it begins with two spacecraft that are, right now, further from home than any object humanity has ever built, running on their last reserves of power, maintained by engineers performing procedures that have never been attempted before, sending back whispers from a place where the sun is just another star. They have been traveling for nearly 49 years. They were designed to last 5, and the story of what is happening to them right now, in these final years of their impossibly long lives, holds the answer to why Voyager 3 may be less a missing sequel and more a monument to a moment that will not come again. Right now, as you listen to this, Voyager 1 is approximately 15 billion miles from Earth. That distance is so large that it resists comprehension. Light itself, the fastest thing in the universe, takes more than 23 hours to cross it. A command sent from the Jet Propulsion Laboratory in Pasadena, California, travels at 186,000 miles per second and still does not reach the spacecraft until the following day. The reply, if one comes, takes another 23 hours to return. A single round-trip conversation with Voyager 1 requires nearly 2 full days. Voyager 2 is somewhat closer, roughly 13 billion miles out, but headed in a different direction. Between them, the two spacecraft define a thin, expanding bubble of human presence in a galaxy that is 100,000 light-years across. The bubble is almost immeasurably small. It does not even extend to the nearest star, but it exists, and the machines that created it are still, as of this moment, alive. That word alive requires some qualification. Voyager 1 now operates on 2 functioning science instruments out of the 10 it carried at launch. The plasma wave subsystem, which listens to the vibrations of charged particles in the interstellar medium, and the magnetometer, which measures the magnetic field of the space between the stars. 8 other instruments have been shut down over the decades to conserve power. The most recent to go was the low-energy charged particles experiment, which was deactivated in April 2026 after the spacecraft's power levels dropped unexpectedly during a routine maneuver in late February. The same instrument on Voyager 2 had been turned off in March 2025. Each shutdown is a small death, an irreversible closing of a window that had been open since 1977. The instruments are not broken, they still work. But the spacecraft does not have enough electricity to run them. The 3 radioisotope thermoelectric generators that power each Voyager convert the heat of decaying plutonium-238 into electricity. At launch, they produced roughly 470 watts combined. Plutonium-238 has a half-life of 87.7 years, which means the power output declines at a rate of approximately 4 watts per year. After nearly 49 years, the generators are producing so little electricity that the engineering team must make agonizing decisions about which systems to keep running and which to sacrifice. The current plan involves a procedure the team has nicknamed the Big Bang. It is a coordinated swap of multiple powered components all at once, replacing older systems with lower power alternatives in a single, carefully orchestrated maneuver. The goal is to keep at least one science instrument operating on each spacecraft into the early 2030s. Voyager 2, which has slightly more power and is closer to Earth, will serve as the test subject. The Big Bang procedure is scheduled for May and June 2026. If it works, the team will attempt the same maneuver on Voyager 1 no sooner than July. If that succeeds, there is even a slim possibility that some previously deactivated instruments could be restarted. Think about what that means. Nearly half a century after launch, a small team of engineers in Southern California is devising software patches and power management strategies for spacecraft that are older than most of the people working on them. Some of the engineers maintaining the Voyagers today were not born when the spacecraft launched. The institutional knowledge required to operate these machines has been passed down across generations like an oral tradition. Except the tradition involves debugging 49-year-old flight software written in assembly language for computers with 69 kilobytes of memory. And the situation became even more precarious in 2025 and early 2026. Deep Space Station 43, the 70-meter antenna at the Canberra Deep Space Communication Complex in Australia, is the only antenna on Earth capable of sending commands to either Voyager spacecraft. Between May 2025 and February 2026, it was taken offline for major upgrades, with only limited operational windows in August and December 2025. During those months, engineers had to complete critical maintenance on the spacecraft within narrow communication windows, knowing that if anything went wrong between windows, they might not be able to respond in time. This is the reality of deep space exploration at its most extreme. The most distant human-made objects in existence, the most successful robotic explorers ever built, are being kept alive by a handful of people using a single aging antenna half a world away, making decisions measured in watts about machines that are running on fumes 15 billion miles from home. There is something simultaneously magnificent and heartbreaking about it. The ambition is staggering. The fragility is absolute, and it is precisely this combination of ambition and fragility that defines the real answer to why Voyager 3 was never built. Because what the Voyager story reveals, when you strip away the technical details and the budget numbers and the orbital mechanics, is something about the nature of great exploration itself, something that most people do not want to hear. Great exploration is not a ladder. It is not a sequence of steps where each achievement leads naturally to the next, where progress moves steadily upward, where the only question is how quickly we climb. That is the story we tell ourselves. We went to the moon, so next we go to Mars. We sent Voyager to the outer planets, so next we send Voyager 3. We explored the solar system, so next we explore the stars. Each step follows logically from the one before. The trajectory is upward. The momentum is inevitable. But that is not what actually happens. What actually happens is that great exploration occurs in peaks. Specific moments when a rare convergence of political will, technological readiness, funding, institutional capacity, scientific opportunity, and historical circumstance creates a window of possibility that opens briefly and then closes. The achievements that emerge from those windows are not stepping stones, they are summits. And the defining characteristic of a summit is that the path goes down on the other side. Apollo was a summit. The combination of Cold War competition, presidential commitment, congressional funding at over 4% of the federal budget, an aerospace workforce swollen by military contracts, and a national mood that treated space supremacy as a matter of survival created a window in which human beings walked on the moon 6 times between 1969 and 1972. Then the window closed. The political urgency dissipated. The funding collapsed. The workforce scattered. And more than 50 years later, as of this recording, no human being has returned to the lunar surface. The Artemis program is working toward that goal, but it has been delayed repeatedly, and its future beyond the initial missions remains uncertain. Voyager was a summit of a different kind. The convergence that made it possible was not primarily political. It was physical, institutional, and historical, each element arriving at the right moment through forces that were largely independent of each other. Start with the physics. The planetary alignment that Flandro discovered in 1964 was a geometric accident. The outer planets do not arrange themselves for human convenience. The specific configuration that allowed a single spacecraft to visit all 4 giant planets using gravity assists was available for roughly 10 years in the late 70s and 80s. Before that window, the trajectory was not possible. After it closed, it would not open again for approximately 175 years. The alignment was not earned. It was not created by human effort or ingenuity. It simply existed, briefly, and then it was gone. Now add the institutional infrastructure. JPL in the 1970s was staffed by engineers and scientists who had spent the previous decade flying planetary missions at an extraordinary pace. Mariner 2 to Venus in 1962, Mariner 4 to Mars in 1965, Mariner 5 to Venus in 1967, Mariner 6 and 7 to Mars in 1969, Mariner 9 to Mars orbit in 1971, Mariner 10 to Mercury via Venus in 1973, the Pioneer missions to Jupiter and Saturn. This generation of mission designers had accumulated a depth of practical experience in deep space navigation, spacecraft engineering, and mission operations that was historically unique. They knew how to build probes that worked because they had been building them non-stop for 15 years. That workforce was a product of the Apollo-era funding surge. When the funding declined, the workforce shrank. The experience base that made Voyager possible was not renewable. It was a one-time asset created by a one-time historical circumstance. Then there was the plutonium. The radioisotope thermoelectric generators that powered both Voyagers used plutonium-238, produced by the United States nuclear weapons complex. During the Cold War, production was robust and reliable. NASA could request the material it needed with reasonable confidence that it would be available. After domestic production ceased in 1988, the supply chain fractured. For decades, NASA depended on dwindling stockpiles and Russian imports. The restart of production at Oak Ridge in 2015 has improved the situation, but current output is measured in single-digit kilograms per year, enough to support 1 or 2 missions at a time, but nowhere near the abundance of the weapons-era supply. The fuel that powered Voyager was a byproduct of geopolitical confrontation. When the confrontation eased, the fuel supply dried up. The Deep Space Network was another inheritance from the space race era, built to support Mercury, Gemini, Apollo, and the early planetary programs. The DSN's 3 global complexes provided the communication infrastructure that allowed Voyager to transmit data across billions of miles. The network was already in place when Voyager was designed. No new facilities had to be built. No new antennas had to be funded and constructed specifically for the mission. Voyager plugged into an existing system that had been paid for by earlier programs. Today, that same network supports dozens of missions simultaneously and is operating near capacity. Adding a 20-year Grand Tour mission to the manifest would require either significant expansion of the network or the displacement of other missions from the schedule. Neither is easy or cheap. And finally, there was the political and cultural context. Voyager was proposed and approved during a period when the memory of Apollo was still fresh, when the space program still carried enormous public prestige, and when Congress was willing to fund ambitious planetary science, even as NASA's overall budget declined. The Cold War provided a background motivation that made space exploration feel strategically important, not just scientifically interesting. The public imagination was primed for grand voyages into the unknown. Carl Sagan, who served on the Voyager imaging team and chaired the committee that created the Golden Records, was one of the most effective science communicators in history. His ability to translate the Voyager discoveries into language that moved ordinary people helped sustain public interest across the 12 years of the primary mission. Each of these factors, the alignment, the workforce, the plutonium, the communication network, the political context, the cultural moment, was independent of the others. None was caused by any of the rest, and none was permanent. The alignment was a quirk of orbital mechanics. The workforce was a legacy of Cold War spending. The plutonium was a byproduct of weapons production. The network was infrastructure built for Apollo. The political will was a residue of the space race. They all happened to be present at the same time, in the same place, in the right configuration to make Voyager possible, and then, one by one, they dispersed. This is the pattern that the absence of Voyager 3 illuminates. Not a story of institutional failure or lack of imagination, but a deeper truth about how civilizations achieve their greatest exploratory feats. The conditions that enable such achievements are not permanent features of a society. They are transient convergences. They assemble themselves through processes that are partly deliberate and partly accidental, and they disassemble themselves through equally uncontrollable forces. The window opens. The achievement is made. The window closes, and the society is left standing on the other side, wondering why it cannot simply do it again. This is not unique to space exploration. It appears across the full sweep of human history. The great Chinese maritime expeditions of the early 1400s, led by the Admiral Zheng He, were enabled by a specific convergence of imperial ambition, shipbuilding technology, navigational expertise, and political support under the Yongle Emperor. When the political winds shifted, the expeditions were cancelled, the fleet was dismantled, and the records were largely destroyed. China did not mount comparable voyages again for centuries. The expeditions were not a stepping stone. They were a peak. The Apollo landings followed the same pattern. Enabled by Cold War urgency, presidential commitment, and historically unprecedented funding, they achieved something that seemed, at the time, like the beginning of a permanent human presence on the moon. Instead, they were the summit. The last Apollo mission flew in December 1972. The next crewed landing, if the Artemis program succeeds, will occur more than 50 years later. The gap is not a failure of technology. It is the natural consequence of the conditions that enabled Apollo being temporary rather than permanent. Voyager fits this pattern with almost eerie precision. It was not the beginning of a grand era of outer solar system exploration. It was the peak. The missions that followed, Galileo, Cassini, New Horizons, each fought for its existence through years of budget battles and political uncertainty. Each was approved only after protracted advocacy by the scientific community. Each was a standalone achievement, not a step in a continuous sequence. And each was architecturally different from Voyager, focused rather than sweeping, deep rather than wide, targeted rather than exploratory. The public does not see this pattern clearly because the cultural narrative of progress obscures it. We are taught that exploration moves forward, that each generation goes further than the last, that the arc of discovery bends toward expansion and understanding, and on long timescales, measured in centuries or millennia, that narrative contains real truth. But on human timescales, measured in decades and careers, the reality is more complicated. Exploration moves in surges and retreats, windows open and close. Peaks are reached and then abandoned, sometimes for generations. Voyager 1 will reach a symbolic milestone later in 2026. It will pass one light day from Earth, meaning that light and the radio signals the spacecraft sends will take a full 24 hours to travel from the probe to the antennas that listen for it. One light day, a measurement of distance so large that it requires a unit based on the speed of light to express it. And even at that incomprehensible distance, Voyager 1 is still a trivial fraction of the way to the nearest star. Alpha Centauri is roughly 4.3 light-years away. Voyager 1, traveling at roughly 38,000 miles per hour, would need roughly 70,000 years to cover that distance. The engineers performing the Big Bang power swap this year are not trying to reach the stars. They are trying to keep two aging machines alive long enough to squeeze a few more years of data from the interstellar medium, the plasma wave subsystem on Voyager. One can hear the density of the space between the stars by listening to oscillations in the ionized gas that fills it. The magnetometer can measure the magnetic field that pervades interstellar space. These are measurements that no other instrument in existence can make, because no other instrument is where these spacecraft are. When the Voyagers finally go silent, that data stream will end, and it will not resume until another spacecraft reaches interstellar space, which, at current pace, may not happen for decades. The proposed interstellar probe, if it is approved, funded, built, and launched in the late 2030s, would reach the heliopause in roughly 16 years, arriving in interstellar space around the mid-2050s. That is an optimistic timeline. It assumes that the concept survives the next decadal survey, that funding is appropriated by Congress, that the spacecraft is developed on schedule, and that the launch vehicle and trajectory work as planned. Each of these steps is uncertain. Many proposed missions have failed at one or more of them. Between the Voyagers going silent and the interstellar probe, if it flies, reaching interstellar space, there could be a gap of 20 to 30 years during which no human-made instrument is operating beyond the heliosphere, 3 decades of silence from the space between the stars. And during that silence, the only data we will have from interstellar space will be the data the Voyagers collected, returned, and stored before their power ran out. This gap is not inevitable. It could be shortened by earlier missions or unexpected extensions of the Voyagers' lifetimes. But it is likely, and it serves as a reminder that exploration is not continuous. It stutters, it pauses, it sometimes goes backward. The frontier Voyager opened may close before the next mission arrives to reopen it. There is a tendency, when confronting these realities, to reach for bitterness, to blame NASA for timidity, or Congress for short-sightedness, or the public for indifference. The temptation is to construct a narrative of decline in which the bold visionaries of the 1970s have been replaced by cautious bureaucrats who lack the courage to dream on the same scale. That narrative is unfair and largely wrong. The scientists and engineers working on planetary exploration today are every bit as talented, ambitious, and dedicated as their predecessors. Europa Clipper is a marvel of engineering. Dragonfly, a nuclear-powered helicopter designed to fly in the atmosphere of a moon of Saturn at temperatures of -290 degrees Fahrenheit, is one of the most audacious mission concepts ever approved. The Uranus orbiter, if funded, would be the first dedicated mission to an ice giant and would answer questions that have been open since Voyager 2's brief flyby 40 years ago. The people building these missions are not small thinkers. They are working within constraints that the Voyager generation did not face. The real lesson of Voyager 3's absence is not about decline, it is about rarity. About the recognition that some achievements depend on a convergence of conditions so specific and so transient that they cannot be reproduced on demand. The alignment of the planets, the alignment of the budgets, the alignment of the institutional workforce, the fuel supply, the communication infrastructure, and the political will. These things came together once, in the 1970s, in a configuration that allowed 2 spacecraft to be built, launched, and flown across the entire outer solar system. And then the configurations scattered, the planets moved on, the budgets shrank, the workforce turned over, the plutonium supply dried up. The network filled to capacity. The political context shifted from Cold War competition to austerity, from prestige-driven exploration to cost-constrained portfolio management. Each change was individually understandable. Collectively, they closed the window that Voyager had flown through. The most unsettling truth in this entire story is not that NASA failed to build Voyager 3. It is that one of humanity's greatest exploratory achievements may have been the product of a moment so unusual, so dependent on forces beyond any individual's control, that repeating it is genuinely harder than the public imagines. Not impossible, but far, far harder than simply deciding to do it and writing a check. Voyager 1 and Voyager 2 are still out there. They are still moving, still carrying the golden records with their cargo of music and greetings and images from a world that has changed almost beyond recognition since they left it. They will outlast every structure on Earth. Long after the last building has crumbled and the last hard drive has decayed, the Voyagers will still be drifting through the galaxy, silent and cold, carrying the only physical evidence that a species on the 3rd planet of an ordinary star once looked up, wondered what was out there, and found a way to go see. They did not build Voyager 3. Not because they did not want to, not because they were not smart enough, or brave enough, or curious enough, but because the moment that made Voyager possible was rarer than almost anyone understood at the time, and by the time the world realized what it had, the moment was already gone. The planets had moved, the money had shifted, the fuel had run low, the antennas were full. And the window, that narrow, precious, once-in-a-century window through which 2 small machines had sailed into the grandest voyage in human history, had quietly closed behind them. What remains is the data they sent back, the questions they raised, the missions they inspired, and the knowledge that for a few extraordinary years in the late 20th century, everything lined up. Physics, politics, engineering, vision, and sheer stubbornness converged in a way that sent humanity's reach further than it had ever gone before. It was not a beginning. It was not a stepping stone. It was a summit, and the view from the top was more beautiful, more strange, and more humbling than anyone who planned the climb had dared to imagine. Somewhere beyond the heliosphere, in the thin, cold medium between the stars, Voyager 1 is still listening. Its plasma wave subsystem hums with the faint vibrations of interstellar space, translating the density of the void into data that travels 23 hours to reach a 70-meter dish in the Australian desert. The signal is so weak that the power arriving at the antenna is roughly 1/10 of a quadrillionth of a watt. It is the quietest voice in the history of communication, and it is still speaking, for now.